So welcome to the IOE Rough Cut Seminar Series. I'm Bruce Maxwell, the MSU Director of IOE. And today we have Eric Sproles with us from the Department of Earth Science, and he's affiliated with the Snow and Avalanche group there, research group. Eric got a BA degree in Latin American Studies, is
correct?
That right? From Florida State, and then a MS from the University of Oregon, physical geography, and a PhD at Oregon State. So, Oregon guy.
There you go. Transplant.
Yeah. Funny how
actually deep Oregon
like there's a lot of all these Oregon connections here.
We're trying.
It's interesting.
So
Yeah, maybe. Yeah. So Eric is going to talk to us. Well, Eric's research, I guess I should say something about that, combines geospatial analysis with field-based measurements, stable isotope tracers, and models to address real-world challenges of climate impacts on water resources. His research efforts span the climates and cultures of the Western United States and South America, and place an emphasis on transitioning science into actionable information for policy and management. So, looking forward to what you have to say.
There you go.
And welcome, one of our newest affiliates.
Thank you. Yes, I am. I think I don't even know if I'm on the website yet. So
yeah,
thank you. And so the first geography class I took was actually from Kathy Whitlock when I was deciding whether or not to go back. When I was debating whether or not to go back to graduate school, and so I took biogeography from Kathy. So the rest downhill from there, right? So the title. So as you can tell, kind of by the title of my talk, it's going to be looking not just to quantitative data, but also how do we transition that into something we can actually use. And the whole quantitative data is it's in our face in a good way, but the amount of it's literally since 2003. We've we've gone from exabytes to zettabytes. That's really hard to get your head around. And we're doubling that every 2 days, or we're creating what we've created up to 2003 every 2 days. So we have so much new information, so much new data, but how do we get that in the format that we can actually use? How do we transition it from bits and bytes into something we can use? And so we're kind of faced with this big wave of information and computational ability and ideas and problems and questions. But do we get overwhelmed by this? Are we just completely inundated by this new surge of technology and information? And these challenges date back even before this big upswell of information in 2003. And basically just going back to the AAAS presidential speech, and this was he was an entomologist, a butterfly entomologist, and it's basically saying if we really want to advance science, we can't just advance science. We have to work with science, we have to work with information, and we have to work on that social capacity as well. And that's something that's really vital to advance. Not just work within, hey, how do we get our discipline forward, but how do we use our discipline to advance society, to advance societal goals. And so I'm going to talk about a couple ideas of how you can do that. The first place I'm going to start is the Elqui River Basin, which is in northern central Chile. It's about 500 kilometers north of Santiago. So at the coast here, remind myself to use pointers and not, it's hard to be bound to a desk. Pointers, but here at the mouth, you get about 15 to 20 millimeters of precipitation a year. So it's very dry. Up in the mountainous headwaters, where about 80% of the water comes from, you get around 250 millimeters, not a whole lot. It's a very dry place. But there's also a very strong demand for water. About 80% of it goes to agriculture. All those grapes we like to eat in March, April, May come from this region. A lot of oranges as well. And so when I first started, this is when I was working as a research hydrologist at CIASA, which is a research institute based in La Sabina, right at the mouth of the Elqui River here. This area was in a really prolonged drought, 5 to 6 years. The same drought that we were experiencing that you all were experiencing in the northern hemisphere, the southern hemisphere was experiencing as well. So coming on as a research hydrologist with expertise in snow, they really wanted some ideas of how they could better manage these situations. They had a nascent monitoring network going on that they had installed, but they really hadn't figured out how to get these field-based measurements into something that was actually actionable. And again, you don't really have to have a degree in statistics to see that this 6 years below average is really not a good thing when it comes to stream flow. Similarly, the reservoir levels were beginning to plummet. Basically, again, you don't need to be a dam operator to know that when you go from almost full capacity down to almost zero, it presents a lot of challenges that are really, really vexing and hard to solve. So the dam managers came to me, the water resource managers also manage the dams, and they said, can you please help us try to figure out a better way to understand how much water is going to be coming down the pipe? We have models and they work okay, but we don't have any measurements way up in the high Cordillera and the upper parts of those watersheds. Well, this is a challenge because there was no data, and when you're asking, there's no field data. So put our heads together and try to come up with an idea. Now, fortunately, this region is blessed with clear skies, beautiful skies, the clear skies, some of the clearest skies in the world. And so it works really well to see the seasonal changes in snowpack. And so this is it. So I started working with some colleagues down there and try to conceptualize a model where we could begin to look at, can we use the changes in snow-covered area, not the amount of water, but the changes in snow-covered area as a proxy for precipitation, as a substitute for that field-based data that we did not have. And so the model that we kind of conceptualized, it was very simple and very straightforward. We basically just using the previous month's stream flow, so multiple months up to 12 months before, and then the monthly snow cover frequency. And from that, we kind of devised a model and a prediction to have the next month's stream flow. So you would run the model for the month of September to have a better idea of what's going on for the month of October. That was our idea. We had no idea if it would work or not. So before I get into the model, I talked about snow cover frequency, and I want to go over just a little more detail on this because this will come through the course of my presentation, the talk today, quite a bit. So snow cover frequency is a really complicated metric. It's simply the amount of observations for an individual grid cell for a MODIS satellite image that have snow in it versus the number of valid observations. So it's simply a percentage. So for Bridger Bowl for January, it'd be a 1. Basically, it's going to have snow the entire year. For August, it's going to be 0. So you can, and it's somewhere of a fluctuation in between. We also have a cloud mask implemented, so cloudy days are not factored into that. And it's at a 500-meter resolution. So basically, kind of just the simple math of it, we have one day, for a whole month, it goes from 1 to 28 for February. You have the valid pixels, the ones that have snow, that don't have snow, and that provides a simple ratio. 0 meaning snow-free, 1 meaning, or 0 meaning no snow at that grid cell for the entire month, 1 meaning it was snow-covered for the entire month. And then from that, you can begin to do a spatial average. We are focused more on a watershed scale, so with that, you can have a spatial average. You can say, hey, the upper portions of the Elky River watershed, had 75% snow cover for the month of September. All right, does that make sense?
What's the time span that you're making this measurement? How many years of data do you have?
2002, the MODIS record goes back. But our Streamflow data only goes back to 2004. So it ends up that this model worked exceedingly well, kind of so well that we looked at it and we went, oh my God, did this really happen? It worked. So we had a Nash-Sutcliffe efficiency, which is Nash-Sutcliffe is basically, it's an index for hydrologic modeling. And so it goes from 0 to 1, 1 meaning it's a perfect fit. So 0.83 was a really high index of a really high skill level. Basically, got a B-, which using relatively sparse data, it was a big improvement. And it was a big improvement from the information and the data that, or I should say the models that the actual water resource managers were using. So it was a big step forward. And it was immediately began to be, the resource manager said, hey, that's awesome. Can you provide us a monthly forecast to see how much water is going to be coming down from the headwaters where we don't have any data? Well, that's great. But that introduced a lot of challenges. One, we have a new task, a new workflow that we have to deal with. And it meant downloading 2 MODIS tiles, two MODIS satellite images. They come in tiles for an entire month, rerunning the calculations, rerunning the model, and the whole thing. And this was on an internet connection that was not exactly robust and dependable and fairly slow. And so it presented a lot of challenges. And so lots of times it took, you know, for us to make the Streamflow prediction, it took about 4 or 5 days of human resource time to get that prediction going. That's a big challenge, and that's a big ask. They weren't supplying funding for it. They were asking us, and man, to take up 5 days of human resource time, that's really hard. And so it kind of, this kind of thing that keeps getting pushed back. Like, we don't need, you know, things move to the front of the line, so that kind of keeps getting pushed back. And as a North American living in Chile, where you're working with some really amazingly smart people, and they have some really technological challenges. As my Chileno friends like to say, we're a country in transition. They aren't quite, first world some qualities and, you know, internet connections in the northern part, not so much. And I think what that really led me to understand is that as a North American scientist, that we kind of have blind spots. Is that working in a place at a lab where you know, I was upset that I didn't have the presenter view today, and that's, you know, small potatoes. But imagine trying to work in a place where you don't even know if you're going to be able to get your data or download it, or it's so we have biases that a lot of our science introduces. We produce science that's replicable in the world that we know, but it doesn't necessarily translate to other places. But I think that also, those challenges also present opportunities. And so at this time, I kind of was wrapping up and moved back to the US and started working with some former colleagues at Oregon State University. They had some ideas on using cloud computing. And they had some ideas of cloud computing, but didn't really have a project of how to use it. And I said, ooh, I have a really good idea. Let's see if we can move this forward. And so one of the ideas with cloud computing, it sounds, you know, as you can kind of become geeked out on cloud computing and then get into, you know, the bits and bytes and the technology, cloud computing has big social possibilities. It can really provide science to a lot of people that didn't necessarily have it. And I'll show you how. So we developed, we presented, we were funded by the Earth Science Information Partners as well as NASA. We partnered up with the Institute for, IPE is Institute for Ecology in the Pyrenees, and then also at Oregon State and my colleagues also in Chile. And so we developed a cloud-based framework to run this same model, the same hydrologic model. And the way our goal was simply to, all those calculations that we had to do, download all the data, reproject it, get it lined up, do all the calculations, make sure it fits for a watershed, transition that, you know, extract the data, and then run the model. We wanted to see if we could do that entirely in a cloud-based format. And that's what we did. We tried, and we used Google Earth Engine. It was something that some friends, some colleagues of mine at Oregon State were already looking under the hood at. And so we really went forward on that front. And we tested this model, this project, in 3 different watersheds around the world, in 3 distinct climates. We picked them with intent. We knew that the model worked in the headwaters of the Elqui River in La Laguna. We also wanted to test it where it's almost pretty entirely snow. We also tested in the John Day River, which is in the eastern slope of the Oregon Cascades. It has a mix of rain and snow, but is pretty much snow dominant. And then we finally tested it in the Rio Aragon, which is in the Spanish Pyrenees. And this is, they have quite a bit of summer rain. So we wanted to test it in 3 distinct environments, really to see where the model worked, where it didn't work, so we could move it forward. So we developed this cloud-based framework, which I'll show you in just a bit, but here are the results. And not surprisingly, in La Laguna, where we knew it would work, this cloud-based format, it worked great. Actually, it improved in using this cloud-based format because we wrote a better script for cloud to mask out the influence of cloud. So we actually made a more robust prediction. It worked marginally well Again, sorry, I was going to walk over. So it worked quite well in La Laguna, Nash Sutcliffe of 0.87, 0.52 in the John Day, where you have a rain-snow mix, and not so well where you have the summer rainfall in northern Spain. We also were able to, we also coded so that for each month, it would give a range of snow metrics for water resource managers, because they would be able to go look at, you know, what did snowpack look like in the Rio Aragon in February of 2016. So it actually give them those metrics as well as an output. And again, the snow calculations as well as the model were all run within a cloud-based environment. The entire thing took about 10 minutes to do from beginning to end. I mean, once we had the code run to do a whole month's prediction takes about 10 minutes. So we went from 4 or 5 days of 2 people working on it to 10 minutes. And that's where to me, how you can really begin to use cloud computing to advance. It allows, well, I'll get to what it allows in a second. But it really moved this whole process forward, and we could give it to the water resource managers in Chile, and they use it, they run it, and they're able to get their predictions within 10 minutes. We have extracted ourselves from the situation, not the situation, but from the process completely. But we weren't just building these tools to try to build a better mousetrap. What we really wanted to do, another component of it, we really wanted to understand is how valuable are these tools? Will people use them? Do people care? And so in addition to just running the model, we also set up a series of we sent the model out to water resource professionals in the United States, Spain, and Chile, and we developed a dual language survey that we sent out to water resource professionals. They're exactly the same. I had my Spanish colleagues make sure that my Spanish wasn't too gringo eyes, but it worked. Oops. And it turns out that people, so first of all, our user base is, you know, with relation to water resources, it was a fairly experienced group of water resource professionals. They had, I believe, the mean water they had was 9.5 years for the English speakers and 12 years for the Spanish speakers. So it was a pretty experienced bunch of water resource professionals. I need to stop using that. There. And so, but even though they were experienced at water resource professionals, they're experienced using cloud-based computing and kind of these next generation tools was somewhat limited. And so this was also kind of key. So we had we had water resource professionals and hydrologists had a really high skill level, but we're still, they weren't quite up to, which is understandable, to using those tools. But what they did find is, even without, is they found these tools to be extremely helpful, and that they were useful, that they would be used in the future, both to calculate snow cover frequency and also to predict stream flow. And that again, even though they might not have the high level of understanding of cloud-based computing and the tools that go with it, they did see the utility and the opportunity that existed within these tools. And they also were highly likely to recommend them. So you can see the end values on this are not overwhelming. This was meant to be a kind of a, it was a seed funded project. So I think you should look at these results, these survey results, as indicative, much more than conclusive. So I think that's a very important, not a caveat, but point of detail, point of relevance. But overall, the feedback we got was highly positive. And kind of the take homes was that even though these users might not have experience with the cloud-based tools, is that they were ready for this next wave of cloud-based tools that we were presenting. But what they really liked was the simplicity that the modeling framework we provided. They were able to, it was a robust model that operated within a web browser. And so they never had to download software. They never had to worry about security patches. Everything runs within the Chrome web browser. And that was a really critical point. They said, we can't buy new software. We don't want to learn new software. We know how to use a Chrome browser, and we know how to use a spreadsheet. We basically had a spreadsheet embedded in there. And the tools need to help tell a story and to help solve a problem. They said these tools are great, but we need to have a distinct purpose in order to use them and the training. So those were kind of the take home, and these were from the qualitative comments that we received as well. So yeah, so we overcame a lot of those challenges, and we've looked and found some opportunities. But I think what you also is the ability to look for collaborative scientific research. And with this, you can begin to use these same, there was what I just presented was more of an applied problem. But I think you can really begin to use these same tools, these same computational resources to develop and then test hypotheses in a way, and the cloud-based tools make it much faster for you to be able to do it. And I'll give you a case, an example. So like any good story, it starts with a hole in the ground, literally a hole in the ground. So this is a well located a little lower in the same Elky River Valley. So you can see it's below the transitional snow zone. So there would never be any snow on the ground, but some in the upper reaches. And also, like any good hydrologic water resource story, is not complete without an observatory and a dry creek bed. And so this dry creek bed, the Quebrada San Carlos, this is what it looks like, and this is where the well is. The last time it had water running in it was in 2002. And the reason I was contacted by this well was that the folks that run this Gemini Observatory, they are in the process of building, they were in the process of planning on building a huge, even larger telescope, large synoptic scale telescope, the LSST. And in order to build a really big telescope, you need a really big lens. And in order to have a really big lens, you need a really big concrete footprint to hold it in place. And in order to build a really big concrete footprint, you need a lot of water. And so this well was the sole source of water for these two multi-billion-dollar observatories. And they said, well, we want some help with this aquifer. And I said, well, that's not my specialty, but I'll see what we can do. I said, what kind of data do we have? We said, we have one data point from 1970. Now that's not big data. That's very little data. So we went out and we measured this well. And in 1970, the measurement was around 19 meters deep down to water level. We went back, and this was at the end of that drought, at the end of that 5 or 6 year drought. And we were all crossed our fingers, and we dropped the piezometer down there, and at 19 meters, it went off. The water level was exactly the same. And this is after a 6 year drought. Okay, and they asked me what my expert opinion was. I said, my expert opinion is you're really lucky. Because we have no idea what happened between 1970 and 2015. But we do know that it's at the same level. And I said, don't use this water to build your big telescope because it's going to go away. But I also made some recommendations. You should put in a monitoring system, pressure transducer, that you can begin to monitor groundwater level flows. And they said, that's great. Will you go out and set it up for me? I said, that's perfect. I'll do it. No problem. They gave we had a nice setup. And it ended up during this drought, the drought ended after we had that pressure transducer. And that river, that creek bed that hadn't flowed since 2002, it was a rushing torrent twice that same winter. And so we had precipitation of 75 millimeters and 68 millimeters twice, which was a lot for there. It's more like that. I was going centimeters, so I was converting my head, right? So about 75 and 68, something like that. But it washed out roads and everything. And as a hydrologist, I said, woohoo, I got that pressure transducer just in time. We're going to see how much it recharges. And I went, it didn't budge at all. There's no change whatsoever at the groundwater levels. I said, what? That makes no sense. At the same time, I had a project going with the University of Aberdeen, and we were trying to develop kind of an isotopical landscape of the water, the source water in the entire Elky River Basin. So I said, well, that's perfect. I have the connections with the lab, and we had some rain samples from those big storms at the exact same elevation as this well. So I'm going to go grab some well water, and we'll see where it comes from. And And so basically the way stable isotopes work is on the relationship between heavy hydrogen isotopes and heavy oxygen isotopes. And so all precipitation falls along this global meteoric waterline. And so the closer and warmer, the closer to the coast and warmer, you're typically going to be at a lower altitude. I'm sorry. You get it when you're at this end of the plot, you're typically going to be at a lower altitude, also meaning you're closer to the coast and warmer generally. Whereas if it's more depleted or towards the left side of the graph, it's going to be cooler, higher altitude, and further inland. So those are just kind of, we won't go, this is not going to be in depth on stable isotope hydrology. But basically, not surprisingly, is that the well water had a very strong isotopic, very similar isotopic signal to the precipitation. That is not surprising because it rained and the rain goes down and percolates and fills up the well. So we just established some good baseline conditions. So all's well, we're continuing to monitor. I'm telling the folks that the work, I said, don't get your hopes up. The well didn't change. Just, I don't understand exactly what's going on. Maybe in time, more data will go. So on and on, we wait for a few months. Nothing's happening. And then all of a sudden, this is blocking, I apologize. But basically the rainstorms were in August, and sometime in November, the water in the well levels went up by 5 meters. So you have two massive rain events for the region, nothing happens. 4 months later, the water goes up 5 meters. That's a lot. That's a lot. And so I said, aha, the snow melted. It's coming down. So we're gonna see a big snow signal in this. So I went and took an isotopic sample, shipped it off to Scotland. It's exactly the same, right? The water in the well was even more like that local precipitation. So the water went up by 5 meters, but it was rain. It was local rain. So scratched my head, had a couple Skype calls with the collaborators and could not figure out. And we said it has to be snow. And so what we conceptualized is that, this one's gonna be really hard to do with a pointer. So what we conceptualized that, so here's our, right in this kind of this pre-Cordillera areas where the well is. And so basically the kind of the conceptual working hypothesis is that water moved down as snow melted and it moved through deep flow paths into these bigger agricultural valleys. That was the working hypothesis. But what we were seeing totally, that did not work. So what we did was to kind of test this hypothesis is we wanted to see how far out snow actually would have to come from to recharge this well. We knew that there was no snow locally, but was it 10 kilometers? Was it 30 kilometers? Was it 40? Was it 50? And so that's exactly what we wanted to do, is we wanted to begin to look at the spatial controls and try to figure out where that snow was actually coming from, to try to understand those deep groundwater flow pathways. And that this is something that would be really, really hard to do with a traditional computing network. You'd be having to download all images, reproject it across multiple years, and it would create a huge headache. What we were able to do using the same cloud-based computing environment that we use with SnowCloud was simply write a few lines of code, and it was able to calculate snow cover frequency. So this is what our SnowCloud framework looks like behind the scenes. Here's a quick, is it gonna let me play the video? Let's see if I can get the video to play. Okay, so again, you can see it's just a web-based browser. Here's all the code. It's about 150 lines of code, including comments. And the map browser, simply hit run. And it's computing the distance at 90 kilometers. This is in real time. Well, this was in real time. So this is calculating, hitting all the MODIS snow cover, all the MODIS data, making the snow cover frequency calculations. You can see it goes from a period of 5 to 10 days into as long as this video lasts, and it allows you to export those tiles straight out. So what that allowed us to do was to test a hypothesis, to get around those technical hurdles that would have taken months to really get everything lined up, download the data, get reprojected, write the code, get it processed. It allowed, with 150 lines of code, I did it in an afternoon. And so what we were able to see is that the snow comes from, we're estimating that really comes from further than 50 kilometers away. So here you have the groundwater level, same green dots with groundwater levels. Here's a big uptick. And then you on the secondary y-axis, you have snow-covered area in square kilometers. So this is from the radius of 50 kilometers. You can see that you have a bit of a blip, but it's really not a big push. And what you can really see, it doesn't begin to, you don't really see, this is our estimation until about 70 kilometers out and even 90 kilometers out is when you really see the influence of snowmelt pushing the water through the system. So this is something that we're writing up. We're also looking at trying to coordinate these same areas with known faults. So I look forward to working with some geologists, some structural geologists trying to figure out the deep fault network in this region. But this is, well, it's in prep. We're working and hopefully have it ready by the end of September. But basically what we've done is we've revised the working model that the deep flow paths move this way, and it's about 70 to 90 kilometers away is where that pressure is happening. And even though in that well, we're seeing local groundwater, what we're seeing is the pressure groundwater. But groundwater is primarily influenced by pressure, not by necessarily gradient. And so our working hypothesis now is that as that snow melts, especially bigger snowpacks, is that snow melts and it provides, it's just a pump, just like you would get just like a pump on a bicycle, you push it down. It's the same principle, is that water is moving down and it's pushing the water out and then the local water up. So what is changing is we're able to see, basically our goal is to revise this working model, and that 70 to 90 kilometers away where the big structural faults are is where it is influencing the local groundwater levels. And this is also something that we've heard from farmers in the area as well. So the next goal, once we get this published, is to try to, or submit it and hopefully publish, is to get a little better dating techniques on that water to figure out where it's coming from. But we have to get it published first. So kind of the point of coming back is that even if I had one data point from 1970, and if all you do is, just focus on what's going on in this well, hey, it came up, it must be from snowpack, all this, but we integrated multiple data sets, these well data, isotopic data, remote sensing data, developed a new conceptual model that hopefully will begin to solidify and influence management in the region. This also has management implications as well, because, all of a sudden farmers are, they're looking at snowpack, even if they don't have any snow in their river valley. And that, really don't keep your focus on what's going in, just locally. And that if you can, really, especially bigger implications where you can build a James Bond / Death Star telescope, is that you can really, using these new opportunities that cloud-based computing provides, will really, that data intensive computational challenges are much more accessible. Those calculations I did basically in an afternoon, which they would have taken months to do before, which is, you get to focus more on the science and less on the data wrangling, which is great. So I'm going to shift gears, and I'm going to go back to my first geography course with Professor Kathy Whitlock in biogeography. And we're going to focus on ungulates in the Western US. And so this, prior to joining the faculty here at Montana State, I was working with the Western Association of Fish and Wildlife Agencies and coordinating their science efforts across 14 Western states. Basically, each state kind of worked individually, and my job was to make sure they were working together, to try and make sure they were working together. And so in February, this was all good. We were making some pretty good progress. And in February, Secretary of the Interior Ryan Zinke came out with Secretarial Order 3362. And it really was a big shift in how we perceive, or I should say a big shift, but it really put a focus on how we look at migration corridors for ungulates. And so basically the premise of this is that as the West expands with regards to population, is it's really impacting the habitat and the winter habitat in particular, as well as the migration corridors for large ungulates Here they call it big game. So it depends on whether you're a wildlife conservationist or in fish and wildlife management. But basically, the goal was really to better understand how animals are moving across the landscape, where they're moving, and how to prioritize management strategies that go into that. And so I began to work with kind of the higher ups across 7 Western states. And this quote really rung out to me. This probably not, it's kind of a paraphrase, but here local. And basically, you know, if we really want to get a handle on migration, whether it be large ungulate or anything, it's really a factor of human migration and how we begin to occupy the landscape or don't occupy the landscape, or how we manage the landscape. And that there's data-based or data, not database, but if you begin to leverage data to better understand how human migration is impacting animals and animal migration, it's going to allow you to develop much more informed policy and management strategies. Let me show you what I mean. So how do you get big data on ungulates? Well, you put a GPS collar around their neck. And so the technology on this has, you know, before radio collars, you'd send grad students into the field and they'd walk around with radio antennas looking for a mule deer, and hopefully they'd find it. Maybe they'd get a hit every 2 weeks, every 2 months, something like that. Now with GPS data, you can get, they'll collect data, exact location every 2 hours. So you can begin to retrieve these data. And so if you can begin to collar considerable, or as the number of animals that you begin to collar expands, you begin to get a lot of data points. And not just points, but you're able to see how they move across the landscape, what their timing is, what rate they move. And this has been absolutely transformative in the field of wildlife ecology. It also really shows the human impact of wildlife ecology. So these data are from a colleague of mine, Jim Heffelfinger in Arizona. So these are elk, and so this is Arizona. So all of the ones in red were captured, were animals that were collared, or on the left side of Interstate 17. All the green were collared on the right side of Interstate 17. There's a pretty strong pattern, as in there's no animals cross the interstate at all. So these aren't individual animals, these are GPS points as they begin to move around. So this has big impact. I'm not a genetic ecologist, but there's no, you're beginning to isolate herds, there's no interbreeding, you're really limiting your gene pool considerably. And so this allows them to go to the Arizona Department of Transportation and say, we have a problem here. We need to really look at migration corridors moving across this Interstate 17. Likewise, it's also shown that there's a lot of movement where they didn't know. This is a mule deer herd just on the, so I'm not gonna, right, there's the south end of the Grand Canyon, and they move all the way down to just near Flagstaff. They had no idea these deer were moving this far. So again, you start to have all kinds of wildlife corridors that you had no idea that migration was occurring. So basically you have winter habitat, summer habitat. I think it's the other way around, summer habitat, winter habitat. And so you're able to prioritize and make management decisions with the goal of really, that are informed by data, that are informed by actual data that will better, that will improve how we manage game numbers, animal population numbers. So all this came out, the technology that comes out of this comes out from University of Wyoming and Matt Kaufman's group, the Wyoming Migration Initiative. And this is a group that they didn't come up with the GPS collars, but they came up with the spatial analysis that really begins to understand, that really quantifies how these animals move, why they move, what stressors are there, whether it be energy development, whether it be suburban migration into those areas. And so this is a winter range. That goes from just Rock Springs. So this is I-80. Winter range goes all the way up across the Wind Rivers into the summer range just south of Jackson. So this is several hundred animals. It goes about 150, 180 miles, depending on where you start and end. This was unknown of. No one had any idea that this migration was occurring. They saw deer walking around, and people who lived in Pinedale, they saw deer walking around, but they didn't really realize it was part of a 200-mile migration. And so when you begin to get these data and you begin to do the analyses, it allows you to develop also really rich products to understand where the migration is happening. Land ownership, I believe this one crosses over 100 different deeded property boundaries, 40 different deeded property boundaries and 100 different fences, this migration. So it's really, all of a sudden, lights went on and said, wow, we have to rethink the way we manage large ungulates on the Western landscape. And so they've developed this mule deer migration assessment where you can really begin to prioritize habitat on this within this whole migration corridor. And basically, you can say, hey, the problem is at Pinedale. So the town of Pinedale was infringing on these lakes, this glacial lake. People want to have lakefront property, right? But the only problem is they realized that there was about 3,000 to 4,000 animals a year moving through about 1/4 wide swath. And so they were able to go with these data. They were able to go to the Wyoming Department of Fish and Game, as well as nonprofits, and they said, we would like to buy this swath of this 1/4 mile right through here. And they had the money within 6 months, and they closed within a year. They raised $2 million, which is no small task. But they bought the land, they transitioned it, and now they took out the fences. Now these 3,000 to 4,000 animals have a clear path going through Pinedale. And the Pinedale residents like it because they're like, woo, it's kind of a tourist attraction. They actually enjoy it quite a bit. So part of this secretarial order also was a series of workshops. There were 4 of them. We worked with all 7 states within the secretarial order. And the goal of the workshops was to train folks into how to use these spatial analysis tools, but also work with the policymakers so that the policymakers understood how to use data, how to use information, and translate that into policy. We just finished up the last one of these in Bozeman last week. And we had about 80 participants, from wildlife biologists to data analysts to folks who worked for the Montana Department of Transportation, tribes, across the board. We had a wide range of folks. And it was extremely positive. The fact that we had Department of Transportation people there, we had about 4 or 5, that's huge. Because as you can see, transportation is a big component of our human footprint with regards to landscape or wildlife migration. I led a series of focus groups within these workshops with the policymakers to better understand how what tools they needed, what information they needed. And they basically they didn't want just data. They want data in a format that tells a story. They don't care about data. They want to have information that provides a compelling story. And then that allows them to go forward and go to state departments of transportation and say, this is a problem. There's no elk crossing at all in this interstate. We have to start prioritizing an underpass or an overpass. It also allows you to start raising money pretty quick. Without those compelling maps to say, here's the pinch point at Pinedale, they weren't going to raise $2 million. With those compelling maps, they were able to go into Jackson and get that money pretty quick. And they also said that it's really important to reach out beyond your organization. It shouldn't just be the field biologist talking to the GIS person within a division. They need to branch out. They need to be working with State Department of Transportation officials as well as extending to the federal level. And it was great because the person who was leading this effort at the federal level, Casey Stimler, was here and participated in all of them. And these points did not fall on deaf ears. They're being transitioned up to the cabinet level. Elaine Chow, the Secretary of the Department of Transportation, is very keen on providing some funding for transport to address these problems. This is again going up to the presidential level in the cabinet. So these bullet points are maybe not these exact bullet points, but they're moving up to the highest level. So it's a very positive thing, very positive outcome. And also Montana is also, next month, Montana will be hosting a wildlife corridor and Department of Transportation forum. And so the Department of Transportation says, okay, we need to get together with the wildlife biologists. So again, this is transitioning these data and this information into actionable science. It's changing the conversation. It's changing the way things are getting done. And it only gets done because you begin to integrate that quantitative science, those quantitative analyses, that data. But you have to make it personal. You have to make those data tell a story. You have to reach out and you have to talk to other folks. And that's really, really valuable. So I encourage you, as whether you're a senior scientist or whether you're in your first year of graduate school or whether you just walked in off the street, I encourage you to really think about that as you begin to hone your craft or continue to hone your craft. Is, how do you get the most traction on the ground? And this kind of goes back to the initial quote from 2002, is that to really get that value, you have to integrate, you have to really look at advance your scientific understanding. Don't abandon your base science or your base social science, but really use that to couple that with technology, and then use those moving forward to advance social capacity and management. These tools, just in my since I started with taking post-baccalaureate classes with Kathy, I mean, you went from storing things on a 256 megabyte zip disk or something like that, I can't remember what they're called, to now being able to access petabytes of information on a web browser. So that technology is there. The hurdles are gone. And so I encourage you to think big, and how you can leverage that information to support your science. You don't have to become a data scientist, but you can reframe your questions that can access that science. So with that, thanks. And a shameless plug, I'm gonna have in spring, I'm offering a graduate class that does just that. So.
Questions for Eric?
Thank you so much. That was really interesting. I was thinking about your surveys that you did with the managers in South America, and if you could encourage them to incorporate it to its full potential, how often would they need to check it, and what's the best use for it? Would that be doing a management plan for the region, or?
No, because they understand their region. I mean, the water resource managers and the scientists there, they're great. They just don't have access to a lot of the same capacities that we do. So their management plan, I think the information they have, they would retool that management plan, and they're actively doing it. Water resources are pretty, in Spain, not as much, but in Chile, they're pretty contentious. So there's political considerations big time in management plans. Spain's top down, and that's not as challenging. Mm-hmm. Yeah. Sure.
Okay. So it seems like with the Chile model that the snowpack and understanding that really models well with the output at the end,
Mm-hmm.
right? But then there's obviously this isotopic disconnect with what you're seeing in the well,
yep.
Which is really surprising to me, because it seems like at one point that water should mix somewhat. I mean, that it's hard to keep something having an isotopic composition
yep.
that homogeneous. So do you think that they're decoupled the whole way, or just that well is somehow decoupled from the? Are there other wells?
I mean, so we're totally scratching our heads on this, and we're developing I think what we really want to do is try to look at the where the main faults are, try to identify where the faults are. We think where the big vertical flow paths are happening, and where they come out. I think the other thing to do is start to date the water as best we can. Using tritium, which works pretty well in South America. But I don't, and so I think the other way to think, I didn't want to geek out too much on the water resources, but so you think of the celerity of water, which is the speed at which pressure moves through a system, very similar to the way an earthquake. And so basically what we're kind of hypothesizing is that as the snow melts, it's changed the celerity or the rate at which the pressure wave moves through the system. But absolutely, it's going to decouple at some point. Yeah. I mean, but Is that because they were at the end of a 5-year drought? I don't know. You know, maybe that changes, but with, you know, one data point starting in 1970, and then, I mean, I got lucky in putting that sensor in at the time I did, or else we'd have missed it. So yeah, no, it's still very, you know, we hope to advance this kind of conceptual model and then submit a proposal for longer term funding, and then also longer term monitoring, and then also try to data a little better. And hopefully the $1 billion telescopes will provide a little bit. They'll provide a couple sensors. So, yes.
What kinds of things are you thinking about here in this that you really need to
Right. So what am I going to take on? So I'm currently working on a NASA EPSCoR proposal that will look at. So as we all know, it's been a little smoky here the last few summers, which means those, and typically the fires happen in areas that are that have seasonal snowpack, meaning that as they melt, that's basically going to be that is our primary source of water coming through here. And so my question is how does in burned areas, how does the albedo of snow change? Meaning the reflectance does it melt faster? There's been some people that have looked at point-based measurements. I want to do, so there's people have point-based measurements and satellite-based measurements. I want to kind of scale that up and see where it changes and use a drone-based approach. So fly drones over burned areas, measure the albedo, and then apply that into a streamflow forecast model to see what that impacts, or if it does impact. That's one. The other one is I went out to with the grasslands group, folks here, and was really interested in the lodgepole fire burn. And I think I have some ideas on how land management, again, using kind of a big data approach, because we have multiple years of satellite data, and then use that to validate a model that's forward looking and look at a range of management strategies and see how that looks, you know, how that impacts. So if we begin to have controlled burns in central Montana, is that going to mitigate large fires in the future, or what impact does that have?
How does that, I don't understand how it works.
Right. So if you begin to, right. So if an agent-based modeling approach, so basically it's not just so you have a model, you know what works and doesn't work from the physical world, and you can begin to use that validated model and put it into a range of land management strategies, a range of climates. And then what that does, it allows you run thousands and thousands of iterations to see what plays out. And this is something I've done before, looking at fire in the oak savannas in Oregon as well. Yes.
Can you get it? I was wondering this with the first image you showed with like looking at, I think, snow covering area.
Mm-hmm.
Can you get it all at thickness of snow?
No, that's the $1 million question.
So you essentially do have to go out and then get
Well, you can,
core at some point.
Right. So you can. That's one thing now. That's the other component of using drones, is that you can begin to use structure from motion to recreate snowpack. That's the other part of it. But there's really no way to do airborne measurements of snow depth.
Okay.
There's one sensor that does it at NASA JPL, and they use LiDAR, and it's like $1 million a watershed to do per run. So it's not really. I mean, it works great for watersheds above in California, but elsewhere it's not economically feasible.
You were able to in Chile like fit a model so well without really even knowing like how much to know, just about where it's laying.
Yep.
It's crazy.
Yeah. Just use a proxy. I mean, it's a brute. We were shocked too, but it worked well.
Yeah, it's great work.
Yeah, we're surprised. So.
Okay, any other questions? Sir?
Thank you.